But the other thing that I came to really fall in love with at St. John's was the way we do the laboratory program here, because it gets at not just the details of an investigation into the natural world, but also into why that's important, and it allows students and faculty to ask the kind of larger questions of what does make life different, what does make a photon different from an amoeba or something like that, and what makes a photon interesting. You know, what is different about light from other things that look like they're in the physical world. So I really found that St. John's opened up for me a kind of world into the scientific world, the natural world, that I hadn't found anywhere else. Definitely in the laboratory program, our students do the kind of work that I did in graduate school. That is, asking the questions, what would you do next? You know, given this phenomenon, what's important about it? What would be the next step? Why is this person interested in this at all? And those are the sorts of things that, in my experience, you just don't get anywhere else. The comments I get back from the scientists that work with our students, they love them. They're often skeptical at the beginning because our students don't have the kind of typical major area of work that they would get from a student coming from somewhere else. But what they see is that our students have a steep learning curve because of that, but our students read. They actually read the articles that they're given, which I think a lot of students don't do. I mean, I don't think I did when I was an undergraduate doing research. It was too hard, right? It's too hard. But our students read difficult things. So they read the material that they're given, and they ask the questions that other people are afraid to ask. And they think outside the box. It's another comment I get a lot from scientists is our students don't have the blinders on of, well, this is this field, so I need to ask this kind of question. They take the investigation where it's going to go naturally, and they ask the questions, and they learn what they need to know as they go along, so that those sorts of skills they get from the whole program, not just from the laboratory program. St. John's is actually among a fairly small number of undergraduate schools that are looking into doing quantum optics experiments that can be done with undergraduates. It's cutting edge in one way, but in another way it's not cutting edge. It's very fundamental because it's showing the sorts of things that physicists were looking for and were predicting might happen way back in the early to mid-20th century when they were just starting to really think and develop quantum mechanics. So what our students can do now is we have the table set up, and we have a laser that goes to our crystal, which sets up these paired photons. And they can see whether the photon exists or not, right? So the first thing is they learn a lot in junior lab about the wave picture of light, which seems to describe light fairly well in most circumstances. And then what happens is you can put in front of this photon of this laser a little block that has a 50% chance of the light going either straight through it or turning off at a right angle. And so what you can do with the detectors is see, okay, well, what happens? Does the light go through both ways at the same time, like a wave would, just kind of hit it and splash off in both directions? Or does it, like a little particulate photon does it pick one direction and go either straight through or turn to the left and hit the detector there? And so that's the first thing our students can do now is they do that experiment, and they look at the numbers, and they can tell that no, it looks like the little bits of light seem to hit the block of glass and then split off. They either go straight through or to the left. They don't do both. And then the next thing we do is say, okay, well, what if we take the light that's split off in two directions and bring it back together? What happens then? Well, it turns out that the photons are either in one branch or the other, seemingly, but when they hit that second block that they're redirected to, they interfere with each other. And so the way Dirac has us think about it is it's not two photons in there, and you can show that there's only one photon at a time, so that it is interfering with itself. That's the theory that Dirac is telling us to believe, right? So it doesn't pick one or the other, it kind of picks both at the same time and then comes back to where it's redirected and interferes with itself, so that you get this nice interference curve. And our students can see that now, and it's kind of mind-blowing when you really think about it. And if you're just reading about it, it's mind-blowing in one way, but I don't know, you don't quite believe it, it seems to me, until you really see it happen. The practica that we do in the labs, it's really varied. So there's some practica that our students do, like our fish dissection in the freshman year, where really they're just presented with something that they investigate. And it's very, very open-ended. So they're given a fish and they're asked to look at it and figure it out, right? And they're given some tools. And so they cut into it and they try to figure out what's what and what the fish is doing, what its body's doing in various places. And, is there a liver somewhere? But they don't have a picture, right? They don't have a picture saying, this is the intestine and all that sort of thing. So that it really is a kind of exploration into what's in front of them. Then we have other sorts of practica that are more directed, where we really want to see a phenomena in front of us that somebody has described. And one of these that I just did recently with my junior lab students is measuring the speed of light, which I found very exciting because I had no idea you could do this with the kind of stuff we have. But so you have a laser and you direct it to a mirror that's moving, and then it hits that mirror, bounces off to another mirror, and hits the same moving mirror again. And depending on how long that path is, you can get it to hit the mirror once, and then when it bounces back, the mirror has already moved a little bit, if it's rotating fast enough. And so because of that change in angle, and that's going to bounce the light off at a slightly different place. So you can measure that displacement and then use that to calculate the speed of light. So that's a much more directed kind of practicum, and it's showing us, I think a couple of things. First, it's showing us that you can measure light, that light moves. And it's showing us what Maxwell had in mind when he talks about the speed of light. But it's also, I think, just showing us how really elegant an experiment can be. It's just amazing that you can do this with just a couple mirrors and a laser. So they do a lot of practical work in the lab. And then, so that sort of thing, like especially measuring the speed of light, they've been thinking of light as a wave up to that point. And so that's a kind of setup for the quantum optics experiments in the first half of the senior lab, when it looks like you just can't think of light as a wave, strictly speaking. You really have to think of it in some kind of a different way. And so they play a little bit with particle and wave duality, and then we get Dirac's account, which is it's neither particle nor a wave, but something else. So they end up experiencing the quantum optics experiments, which then allow them to kind of see for themselves. So this is, I had my speed of light last year in junior year hitting my mirrors, but it looks like if I look a little more carefully, there's something else going on. And that itself is part of learning about what the scientific enterprise is doing and what it's about. Because it looks very simple if you read an article in the newspaper about what somebody has found. But that is simplifying things to such an extent in pretty much every single case that it's just burying all the complexity. And our students, they encounter the complexity themselves of the natural world, and they get to experience it and fiddle with it and see, can I get my results to look a little cleaner? Is there some technique involved that I need to learn better or not? Is it just that this is a very difficult thing to deal with? So that experience, I think, is just as part and parcel of the whole St. John's experience.